Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the recommendation system, the engine that decides what shows up in your feed, search results, and discovery surfaces on Netflix, YouTube, Amazon, and Spotify. We'll cover candidate generation, two-tower models, ranking, feature stores, re-ranking evaluation, and the trade-offs you need to know for a senior system design interview. Whether you're preparing for a FANG interview or building a recommendation platform at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the recommendation system, the engine that powers the feeds, suggestions, and personalized experiences you see every day on Netflix, YouTube, Amazon, Spotify, Instagram, and LinkedIn. If you have ever wondered how a platform takes millions or even billions of items and surfaces the perfect 10 for a single user in under 100 milliseconds, this video is for you. We'll walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models and algorithms, low-level design, and the trade-offs that show up in a senior system design interview. Whether you are preparing for a FANG interview or building a recommendation platform yourself, let's get into it. Here is the core problem. Modern platforms have catalogs with millions of videos, products, songs, articles, or jobs. Users have limited attention and cannot browse through the entire catalog. At the same time, interaction data is incredibly sparse. A user may have watched only a few hundred videos out of a billion available. New users and new items arrive constantly, creating a cold start problem where we have no history to rely on. There is also a tension between relevance and diversity. Showing only what the user already likes creates a filter bubble and reduces discovery, while showing too many novel items can feel random and hurt engagement. The system must balance real-time personalization with batch model training, respect privacy and consent, and run continuous A/B experiments to prove that a change actually improves business metrics like watch time, clicks, or revenue. Let's walk through the functional requirements. First, the system must generate a manageable set of candidate items from a massive catalog, usually hundreds of items out of millions, using fast retrieval techniques like approximate nearest neighbor search or two-tower models. Second, it must rank those candidates using a scoring model that combines user profile, item features, context, and interaction history. Third, it must be context-aware. Time of day, device, location, session history, and recent real-time events all matter. Fourth, it must handle cold start users and items by falling back to content-based signals, popularity, or onboarding signals. Fifth, it must support re-ranking for diversity, freshness, fairness, business rules, and explainability. Sixth, it must integrate with an experimentation platform so engineers can run A/B tests safely and measure lift. These capabilities make the system both useful and measurable. Now the non-functional requirements. Latency is critical. The entire recommendation request, including candidate generation, feature lookup, ranking, and re-ranking, often must complete within 100 to 200 milliseconds at the 99th percentile. Throughput must be high because a large platform can serve tens of thousands of requests per second. The system must scale horizontally to support hundreds of millions of users and billions of items. Availability must be extremely high, since the feed or homepage is usually the most trafficked surface. Feature freshness matters. Recently watched, clicked, or purchased items should influence the next recommendations quickly. Privacy is essential because recommendations depend on personal behavior data, so we need consent-aware feature engineering, encryption, and access controls. And finally, model serving and training must be observable and debuggable so teams can detect regressions. Here is the high-level system architecture. On the left, the client application sends a recommendation request through an API gateway to a recommendation service. The service first calls candidate generation, which uses a fast retrieval index such as an approximate nearest neighbor index over item embeddings produced by a two-tower model. The retrieved candidates are enriched with features from a feature store that holds user profiles, item metadata, and real-time interaction features. A ranking model scores each candidate and returns a ranked list. A re-ranking layer applies diversity, freshness, fairness, and business rules before the final results are returned to the client. Meanwhile, user interactions are logged into an event stream, which feeds both real-time feature computation and offline model training pipelines. Trained models are published to a model store and served by the candidate generation and ranking services. The key metrics to memorize cold. Online business metrics include click-through rate, conversion rate, watch time, revenue per user, and session engagement. Ranking quality metrics include precision at K, recall at K, normalized discounted cumulative gain, and mean average precision. Catalog health metrics include coverage, which measures how much of the catalog is being recommended, and diversity, which measures how different the recommended items are from each other. Serendipity measures pleasant surprises. System metrics include latency at the 50th and 99th percentiles, request throughput, feature freshness, and model serving error rate. Experimentation metrics include A/B test power, guardrail metric violations, and the percentage of experiments that reach a statistically significant conclusion. These metrics are what interviewers and product teams actually care about. Let's trace the end-to-end user journey. A user opens a streaming app and lands on the home feed. The client sends a recommendation request that includes the user identifier, device type, and a small context payload. The recommendation service calls candidate generation, which retrieves 500 candidate videos from an approximate nearest neighbor index. The feature store enriches these candidates with the user's recent watches and the video's metadata. The ranking model scores each candidate and returns the top 50. The re-ranking layer mixes in a few fresh and diverse picks to avoid a filter bubble, then returns the final list to the client. The user scrolls, clicks on a video, watches for 12 minutes, and likes it. That interaction is logged, updates the user's real-time features within seconds, and is later used to retrain the model. The next time the user opens the feed, the recommendations are even better. The core models and algorithms. Collaborative filtering recommends items based on patterns from many users, using techniques like user-user similarity, item-item similarity, and matrix factorization. Content-based filtering recommends items whose attributes match the user's profile or the items they have liked before. Two-tower models learn separate user and item embeddings so that retrieval can be done by approximate nearest neighbor search in a vector index. Deep learning rankers combine dense embeddings with categorical and continuous features to produce a final score. Embeddings are central to modern recommendation. They compress users, items, and context into dense vectors that capture similarity. Contextual bandits and multi-armed bandits allow the system to explore new items while exploiting known preferences. Finally, an A/B testing framework assigns users to treatment and control groups and measures lift on business metrics. Now the low-level design deep dive. The feature store is the backbone and is usually split into online and offline stores. Online features include the user's recent clicks, watches, and location, while offline features include historical aggregates and pre-computed item embeddings. The request pipeline is: the API gateway receives a request, the candidate generation service fetches candidates from an approximate nearest neighbor index, the feature store joins user and item features, the scoring service runs the ranking model, and the re-ranking service applies business rules and diversity constraints. The response is logged with the request identifier and the ranked items. Interaction events flow through a streaming layer to update real-time features, and through a batch layer to create training examples. Model training is orchestrated as a pipeline that includes data validation, feature engineering, training, evaluation, and a canary deployment step. Key takeaways for your interview. First, always separate candidate generation from ranking. Candidate generation is about fast recall, while ranking is about precise scoring. Second, the two-tower model is the standard modern retrieval architecture, because it lets you serve billions of items with approximate nearest neighbor search. Third, the feature store is the critical infrastructure piece that connects offline training and online serving. Expect detailed questions about freshness and consistency. Fourth, be ready to discuss the trade-off between real-time personalization and batch model training, and when each is appropriate. Fifth, evaluation requires both offline metrics and online A/B tests, because offline metrics can be misleading and do not always translate to business impact. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the recommendation system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the recommendation system. We covered the full picture, from candidate generation and two-tower retrieval, through feature stores, ranking models, re-ranking, A/B testing, and the low-level design of the request pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.